Right, so hello again. Nice to see you here. And this talk, it was labeled as a high load, but it's a cybersecurity talk. Don't trust all the labels. And I have 45 minutes, not 25, but 45, so brace yourself to a lot of cybersecurity content. By the way, as was already mentioned, my name is Anastasiia, and I'm head of security engineering at Cossack Labs. Cossack Labs is British-Ukrainian private commercial cybersecurity company. We are 12 years old and we specialized in cybersecurity. We're working with other companies that have high security requirements like logistics, robotics, AI, ML, but with start of full-scale invasion, we do a lot of defense security work and militech. We are working with Ukrainian Ministry of Defense, with NATO agencies, with Ministry of Defenses of other countries, with many different agencies, armor manufacturers, defense system manufacturers, combat system manufacturers. But as this is a public event for developers, I will not talk about all this nice and shiny defense stuff. My presentation today is ready to be, it's been on video, it will be available publicly, so it's redacted, it's censored and obfuscated a little bit. I will not share you any secret, and sometimes I will talk about things more like on a high level, right, without giving exact examples. Okay, so the main topic is how we build security in a high-stakes, high-risk systems. Do you know what is like mission-critical systems? What are they? They might be different from systems you are building or systems you got used to. We will take a look on these examples today. We will talk about critical national infrastructure, power grids. Power grids, these are huge geographically connected systems. They basically control power plants that generate power and consumptions that use power. And the main part of why power grids are very important from security perspective and why security architecture is different in power grids, that this is a real-time, real-life systems. If something happens with them, you will feel the real-life impact. Then, governmental systems. Another example of high-risk, high-stake, mission-critical system. A lot of, in Ukraine and in Poland, we have a lot of governmental systems that operate on data of users, of citizens. Some systems are being developed by different agencies and different ministers, and they need to exchange data. And we don't want this data to be leaked. So from a security perspective, they pose a threat of how to protect data of many people. Then, another example of mission critical is, of course, situational awareness systems or combat systems that have information on a map, that have very critical information about blue forces, and those systems can use different technologies. They can be built as a web application, mobile application, as a hardware and IoT tools, and they're interconnected and work together and, again, need to exchange sensitive data. And of course, we will not talk, but we will think about drone warfare and systems that control drones, different kind of fleet management tools, drone provisioning pipelines. For those systems, security is as well as important because we have thousands of drones and the systems that need to control them in real time. And I see already that people are making pictures. That's why we don't have any real examples here. No, yeah, please make pictures. I'm just joking around. Yeah, but all these systems are a great example of high stakes, high risks, mission critical system. And security for them is very different from security of typical web applications. Or how I like to explain Instagram for kittens. Right? When we are working on security for them, we understand that these systems, they can be geographically distributed. They can have hundreds or thousands of different devices or stations or deployments. They are working in real life, in real time. They are operating on highly sensitive data, user data, mission data, geolocation of devices. They need to exchange this data through other systems. And the impact of different incidents can be fatal. So security for these kind of systems, it's not a security, it's not a perimeter security, and it's not even a software security. We are talking about data-centric security. We are talking about protecting the sensitive data that these systems operate on, even when this data goes through system to system to system to system. Of course, in security, we don't do things just because. We always have certain goal, what we are protecting. And these are typical security goals of high risks, high stakes systems. We want to protect the data those systems operate. We want to ensure that this data is being exchanged securely among different systems connected to each other. Because trust me, there are a lot of systems connected to each other. We need to ensure not only data confidentiality, but also data authenticity, where it's coming from. Or what is this device? Are we sure that this drone is our drone? Again, not the questions typically raised for Instagram for kittens, right? Then, as many of the systems are connected to each other, the security goal is to prevent cascade effects. We know that one system will have an incident sooner or later. Technical failure or result of cyber attack, but the failure in this system should not lead to failure in other connected systems. Losing one device and having someone to break into this device should not lead to hacking into our internal system. Of course, many of those systems, especially right now in Ukraine, they work on a very poor connectivity. Poor internet connection, power outages, not good, not enough physical networks or like damaged physical networks. That's why we need to ensure that all our security controls can work with the really unstable and degraded networks. Right. And the last part is auditability or transparency or traceability. We need to know in our systems who did what and when. Usually it's done by audit logs. These security goals, of course, these are only like key security goals, the main one. For some systems can have even more. But the main point when we are making certain security decisions, when we are doing certain security controls, we need to understand why we are doing that. Because every security control, every security tool actually increase the attack surface. When we add something, we think for security, we are adding more and more components. In this example, we are adding more and more attack surface. So we need to be really, really precise of what we are adding and why we are adding, what are our goals. Do you know what this is? Who knows? Raise your hand if you know. 1, 2, 3, 4, 5, 10. Okay. So these are the answer. After we answered why, what are our security goals, this is the answer what we are protecting from. This is meter attack matrix, basically a set, a list, or a matrix of different attack scenarios, different threat scenarios, how attackers are breaking into our systems. You see, if you have not heard about meter attack and you are an engineer, you create systems, I really recommend you to go to attackmeter.org and just read it. You can basically select any vector and read more about them. Meter attack, it's not like a statical thing. They update it really often because attackers find new and new ways. But it's a good combination on different techniques used for different kind of systems. And as we are talking about high risk, high stakes, we can be sure that attackers in our case will use some of that. Of course, if meter attack is too complicated, let's talk about OWASP top 10. Please raise your hand if you know what is OWASP top 10. Okay, more people are aware about that. So OWASP top 10, first of all, OWASP is this organization, like community for security, right? So they publish a lot of different cheat sheets, guidelines, and standards to help engineers to build more secure systems. OWASP top 10 is like a tip of the iceberg of the tip of the iceberg. Is the 10 most popular mistakes, 10 most popular risks that software developers are doing in their applications. And usually when we say OWASP top 10, we mean web applications. But OWASP has different top 10s for mobile applications. They have top 10 mobile. They have top 10 for IoT applications. Right now, they are updating OWASP top 10 for web. Again, the most popular thing, tip of the iceberg if you're going into security world. And this new update, 2025, says us that some risks differ from the previous update of 2021. For example, SSRF, server-side request forgery, suddenly it went to the top of the new one, and it's been merged into broken access control. You can see the new thing here. Mishandling of exception conditions. It's just a list of common mistakes and common issues developers see in the applications developer make, or like security engineers see in the applications developer make. If meter attacks matrix is too much, at least look at the OWASP top 10 to understand what are possible mistakes and what are the possible risks in the systems you are building. If OWASP is too few for you, if you want to go deeper, again, to answer a question, what are we building, from what we are protecting, take a look on the different standards, the standards for security people. As I mentioned, OWASP have a lot of different cheat sheets. One of the main things that we are using is OWASP ASVS, which is Application Security Verification Standard for web. OWASP ASVS, Mobile Application Security Verification Standard. OWASP ISMS, Information Security something. OWASP SAMM, Software Assurance Maturity Model. These are different checklists based on the standards that allow you to evaluate the security of your applications, web, mobile, hardware, like IoT applications, or processes. SAMM is a standard to evaluate your security processes, how you create applications, how your development team is working. But OWASP things, they are written for developers. They are very easy to understand, but they are very limited. The real hardcore is happening in NIST standards. And we have a NIST standard for almost everything. My favorite one is, of course, NIST Special Publication 80053. Which is Privacy and Security Controls for Federal Organization. So this is a publication of only 400 pages. It explains and describes 1,100 different security controls that are very useful for your large systems. These are not OWASP level security controls. They are not about input validation. They describe what processes do you need to have, what special features do you need to have. And based on this standard, different security profiles are described. For example, if you're working on defense applications in Ukraine right now, you need to comply, your application, your system need to comply to a security profile for defense application that uses 230 security controls from this list of 1,100. What else? OWASP has different standards for basically everything you do. If you are curious about zero trust, they have a standard for that. If you are curious how to do risk management, how to understand risk and threats, they have a standard for that. If you are working on server-to-server authentication, they have a standard for that. Yeah, only 400 pages usually. Some shorter one are 200 pages. Only 400 pages, and you can read the wisdom of people. And of course, NIST standards are not the deepest. We will see in other examples that you can go even deeper into more specialized architecture. Finally, the topic of our presentation today is all those weird abbreviations. Let's start from the easiest one, Data-Centric Security, DCS. This is an idea that you protect the data that goes from system to system. It means you still need to protect perimeters, you still need to protect infrastructure, you still need to protect software. But the main point is that you protect the data. To protect the data, first you need to label or classify the data, to understand what is the data types and what classifications they have. Is it a sensitive data? Is it worth protecting? Or if it's a public data, you can do nothing with that. And of course, the ultimate data protection measure is encryption. We will talk later about it. Next one, ZTNA, Zero Trust Network Access. Do you know about Zero Trust? Raise your hand. Okay, perfect. Next time you're on the stage. So Zero Trust, it's an idea that we have zero trust to anyone. As a code, as our service, we have zero trust to everyone, to the user, to other services that send requests to us. As a system, we have zero trust to the users that use our system, to the admins that admin our system, to our systems, to other systems that are exchanging data with our system. Basically, zero trust, initially, it's a network configuration idea, but we can use it not only on the network level, but on the API level as well. It means we verify everything. We authenticate and authorize every request from every user, every service. We just don't trust that someone using this IP address is trusted. No. We will soon look on how zero trust looks on practice. Cross-domain security solutions or cross-domain solutions, CDS. Please raise your hand if you heard this one before. 1, 2. Okay, I see the 3. I see the architects here. Okay. So cross-domain security solutions is not a new idea. It's been described more than 10 years ago. The main point is that when your systems are really large, or when you have different kind of systems, they operate on different kind of data. Those data types can have different classification. Secret data, confidential, public data. And you cannot exchange data with different classification levels freely in your system. You need to have something, you need to have a security control. CDS is a security control. It's like a firewall, but not a firewall. You need to have a security control that will check what data type, what data classification is coming from system A, if we can put this data to the system B. The main purpose of CDS is to ensure that we don't accidentally share classified data to the users or other systems. We will see the example of that. By the way, cross-domain security solutions, it's not described in NIST standards. You need to go deeper to read about it. It's described in NSA, yes, NSA, that's NSA, in their Raise the Bar publication. Basically, they say that OWASP, tip of the tip, NIST, and then raise the bar. You kind of go deeper than NIST. And my favorite security control or my favorite security architecture pattern is defense in depth. Do you know what is defense in depth? Please raise your hand. Okay, good, many people. For those who don't know, defense in depth, or it's also called echelonized defenses, is an idea that one security control will fail. You need to have several interconnected, independent security controls that will continue working. Sometimes defense in depth can be implemented by using compensating controls, right? You have main controls and then you have a set of compensating controls. But in a nutshell, defense in depth means that for critical places in your applications, for critical data flows, you need to have several security controls. Sometimes they will duplicate each other, and that's fine. An example, if you're using MDM, mobile device management, right? And if you have your own application that you distribute for your users using MDM, usually in MDM solutions, they already have a check if device is rooted or if device is jailbroken. But in your application, as your developer, in your code, you create the same checks. You also check if device is rooted, if device is jailbroken. Because inside your application, you can use different approaches, you can check different triggers, you can have some custom logic. In this example, MDM solution will do this jailbreak detection check. And your code in your application, once the user will run your application, it will also have the jailbreak check. This is defense in depth, right? Oh, as one of the examples. Let's talk about them deeper. So data-centric security. Again, the idea is that we are protecting data whenever data leaves. And in many cases, it means that we protect confidentiality by using encryption. And we protect authenticity by using signatures or by combining encryption and signing. One of the examples of data-centric security is ALE, application level encryption. Please raise your hand if you heard ALE term before. Okay, good. I feel that this is the correct audience. You will learn at least some new terms today that you can Google, and during all those Christmas and festive nights, you can read the OWASP guidelines and NIST publications to learn more about security. So application level encryption says that you need to have time to make picture here, please. Application level encryption says that encryption happening inside your application. It's your responsibility to encrypt the data inside your code. It works together with other types of encryption. You can see in this example that TLS, transport layer security, is being terminated usually on the gateway or on the operating system level, while application level encryption is being terminated inside your application, inside some particular line of code where you decide to decrypt the data, which means that the data flow is protected for longer. One of the examples of application level encryption is end-to-end encryption, where the data is fully encrypted from a user to user, from a system to system. I think that you have experience before with application level encryption, because in a very simple scenario, it can look like that. Just a JSON model where some sensitive fields are being encrypted, and of course, in our case, encoded because it's JSON, but encrypted first. Application level encryption is a very popular security control, but you need to use it properly. Because where we have encryption, we have key management. And key management is where things are getting complicated. Because you can encrypt the data with the best encryption method there, but if you put the encryption key near the encrypted data, good luck. If you're curious to learn more about application level encryption, many years ago, we wrote a huge article on InfoQ about different usage scenarios for application level encryption, challenges, issues, and how to overcome them. Okay. Another popular example of encryption tools is hybrid public key encryption, HPKE. Please raise your hand who has heard this term before. Okay, 1, 2, 3, 4, 5, 10. Who has used HPKE? I see one hand. Wow, that's cool. We need to talk. HPKE, basically this idea is not new. This idea is that we use typical symmetrical encryption to encrypt the data using random symmetric key, right? But then we encapsulate data encryption key with key encryption key using asymmetric encryption. Hybrid. The idea of hybrid encryption is that the data is encrypted symmetrically, the key is encrypted asymmetrically. It creates so-called envelope, and you can share this data. It provides better guarantees than typical symmetric encryption. Why we are talking about that? Because finally HPKE is getting its own standard. It's still a draft, but sooner or later it will be here, and sooner or later you will see HPKE used almost everywhere. Because people already use it, but they create those envelopes themselves, they select ciphers they like, and finally we have a standard. How these things are used in real life? When we are talking about drones or other kind of systems, we want to share payload too. We encrypt that payload. Payload could be firmware or mission data, any kind of data you want to put on device, right? So on your backend side, you encrypt the data specifically for this device using their public key from their key pair. And yes, the data will be encrypted. The data goes encrypted. You can use TLS, you can use VPN, you can use any kind of transport encryption you like, but the data is already encrypted. So we can say that in some cases, in some parts of the data flow, it will be encrypted twice or even 3 times, and that's okay. We are worried that this data is encrypted for this particular device. When it gets on the device has private key to decrypt the data. This is the main idea of all data encrypted data flows, where data is generated specifically for devices. The encryption methods can be different. We can use different kind of protocols, different kind of ciphers. HPKE is used a lot. Cryptography library H is used a lot. But the idea is that you encrypt something for a particular device. When we want to gather some information from device, some telemetry data, geolocation, or what's happening there, we do the same, but in a different direction. On device, we encrypt this telemetry using public key of our backend services, and we send this encrypted package to our backend. And in this case, we are interested not only into protecting confidentiality of the data, but also into protecting the authenticity of the data, to make sure that this data is coming exactly from this device. You can think about drones that can recognize the objects, drones that have ML models on the board, HML. So when you are sending your specialized ML model on the drone, you want to have it encrypted. And when this ML model recognizes some objects and you send those objects back to your backend infrastructure, you want to have them encrypted. So this kind of encryptions is a good idea, is a good example of data-centric security that is used in IoT in drone warfare. Let's talk about the next one, cross-domain security solutions. In a nutshell, as many of you has not raised your hand, in a nutshell, cross-domain security solution is a security control that helps different systems to exchange data securely. Usually, cross-domain means between different domains, and the domain can be data of certain level of classification, right? If we have data of certain level of classification, usually it means that if data is classified, I need to have a special equipment to reach to classify data. For example, a specialized protected laptop. If the user needs to talk to operate on data of different levels of classification, in the worst case, they will have different laptops for each of these systems. Not the best idea. Cross-domain security solutions says us that we can have a security tool, a security control, like a huge data firewall that will sit in between. It will validate if data can actually reach from this system to this system. It will declassify the data. It will make sure that only data of certain data types, data classes can go to the other system. It will add a lot of filtration and checks if the data is correct, if the user is authorized to use this data, and only then the user can get the access to this data. It's just a security control, again, as a firewall. The trick is that when we have more classified system, let's say top secret, and we need to share some data to a less classified system, let's say secret or confident, we cannot do it directly. We need to have something that will check if those data types can be shared. Right? And that's why we use CDS. Usually, there are different kinds of CDS solutions. Sometimes CDS solutions only check if the data can be shared. Sometimes they have all the features like software-level features, user interfaces, yada yada. In most cases, they are used for office infrastructure to check data labels in your Google Docs. Not Google, but in your internal documentations. In some cases, they are used to check like streaming data, yada, 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 yada. The main features of cross-domain security solutions is that you have all these checks. You cannot just put the data from system to system. In many cases, some of these checks are physical. You can have physical adapters from data from a system with high classification. You can have like a physical adapter that will not allow someone external to connect to the system. It will allow only one directional data flow. Those physical adapters are called link breaks. When we are going to software levels, they are called protocol breaks, meaning that we have different security controls that just to check our data, to validate it, yada, yada, yada. You will see the example. Let's talk about examples. Let's talk about power grids. Do you have any experience in power grid engineering? Well, I tried. I mean, maybe. Okay, none. Okay, in a nutshell, power grid systems is just large systems, but the trick there is a balance, because power generation stations, like coal or nuclear, they can generate certain amount of power, but the problem in a physical world that you cannot store electricity for a long time. Yes, you can have batteries, but you don't have a storage for electricity. So everything that you have generated, you need to use really quickly. In the power grid management, it's very important to have this balance of generation and consumption. That means that for power grid systems, they are basically huge country-level systems with hundreds of substations. You need to have the data flow. You need to understand how much electricity do you generate right now. You need to collect this data very quickly in real time. You need to share this data with your dispatch centers. If your country is large enough, like Poland or Ukraine, you have different substations, different regions, and some central SCADA, some central dispatch. So you need to collect data from power stations and send this data really quickly to your central dispatch system, that this central dispatch system will make a decision if this power plant should continue to generate this amount of power, or we need to decrease it, or we need to increase it. So the central dispatch will send back commands to those power plants. In a very, very simplified version. I'm looking on your eyes. This is a very simplified explanation. The main idea in those systems is that you have a lot of sensitive data. We don't want power plants to explode, that we need to operate on in real time really quickly. But when we talk about engineering, things are simple. If we forget on a second that these are real power plants, real explosions, we just have devices that send telemetry data to central devices, and central devices that send command back to substations. And of course, in these examples, we are interested in protecting confidentiality of data and authenticity of data. The trick in power grid management, you need to understand if you're talking to this particular power station. You need to identify them. Because, you know, one of these classical security attacks, evil twin. Some other device can pretend to be another device. And if you send a command to increase electricity to another power station, to evil twin power station, this is where explosion can happen. So you need not only to protect confidentiality, but to protect the authenticity of data and your devices. Let's not talk about country level, let's talk about one data flow. As these are geographically distributed stations, of course we have some secure protocols between them. Of course we use TLS, of course we use VPN, of course we understand which station we talk to. But that's not enough. Remember zero trust. We cannot trust the station to believe that this is our exact station. We check. And in the simplest way, we are checking if this IP of this power plant is in our allow list. Next, if the VPN certificate of this power plant is expected VPN certificate. Next, if TLS certificate of this power plant is expected TLS certificate. Next, if the application running this power plant is expected application. We are doing these checks one by one, and only then we can make a decision that we can trust, kinda, this power plant and get information from it. So this is an example of how we check using zero trust methods, how we check different configurations before we can receive telemetry data from a power plant, and especially before we send commands to certain power plants. If we look into things even further, we can see that this is a good idea to use cross-domain security solutions, to use all those protocol link breaks, protocol breaks, like a physical breaks to ensure that we cannot send some other commands to our power station. But we will not go there. Let's talk about drones. I still have 6 minutes. Are you already tired, or do you want to continue talking about drones? Okay. I know. We are talking about security things that are a little bit abstract because I cannot show you exact examples, but still, thank you for being with me for 6 more minutes. Let's talk about drone warfare. Another example of security controls is when we want to control drones. And before we control drones, we need to identify drones. And it's not easy as it sounds. Because devices on the sky, they don't have, a flag saying I am your drone or I am a Russian drone. No, we need to have certain ways how to ask this device, how to receive some information from this device to understand if it's ours or not. One of the solutions for this problem is UA Drone ID, which is a protocol and the huge system in Ukraine that allows us to identify our drones and not our drones. And this is the system that we as Cossack Labs helped to build, and it's already working actively since 2023 on a battlefield. The idea here is that we use the same approaches. We use cryptography to ensure that information coming from a drone is signed by certain IDs, by certain keys that we know about. And all these efforts are to show that on the map, yeah, you can see like blue rectangle, not actually rectangle, blue thing on a map. All these efforts, all these drone ID efforts to recognize friend of who is to see on a map in the situational awareness systems that these devices are actually our devices, blue force devices, and not Russian devices. So the people who work, soldiers who work on a battlefield, will not damage or destruct our own drone. But the protocol itself, it's not public yet, that's why I am not giving you any details again. The protocol itself uses all these ideas of zero trust, cross-domain security solutions, and a lot of encryption to ensure to recognize friend of who. Some of the details, by the way, some of the details are public and you can read them on our website without exact answers. But the main idea that every device has certain beacon, cryptographically protected beacon, and all other devices, the ground station, the situational awareness system, they check the cryptographic validity of this beacon. So, encryption, cryptography. If we want to see more complicated architecture schemes, we can say that we don't trust any drone, we don't trust any device. And before we receive information from that device, we check its signatures, we check the information formats, we use all the analytical tools to find if the information is coming from the correct device, if we did have certain issues or anomalies related to this device, yada yada. So basically, in a nutshell, to be able to tell with some degree of certainty that this drone is our drone, we use a combination of cryptography, data DMZ, demilitarized zone, filtering, validation, and connection to CEM, anomaly detection, yada yada. Only to see that this dot is indeed a blue dot on a map. Okay. To wrap up this cool presentation about different security controls, my main idea is that when you are building systems, especially mission-critical systems, not Instagram for kittens, you need to put a lot of thought into selecting proper security controls, into your system design, because the incidents will happen. Technical incidents or cyber attacks, they will happen. And your system is as resilient as you build it, right? Because one security control will fail, but if system will fail, or if the failure of this system will cause a failure of other systems connected to yours, it's your responsibility as an engineer. We learned today a lot of different abbreviations from security. And I have a question for you. So in this slide, let me stand here. In this slide, we have all abbreviations that are related to security except one. Please raise your hand if you think you found the one abbreviation not related to security. And we will check if you're correct or not. Okay, what do you think? That was a good idea, but I don't hear the answer. AAA, authentication, authorization, access control. No, related to security. Another try. Oh. HSM? I pretend I didn't hear your answer because let give them more tries, okay? Who wants to try more? Which abbreviation is not related to security? Okay. IRP, Incident Response and Protection System. Yes. SBOM, Software Bill of Materials. Basically, it's a list of different software components, libraries that you use in your system. SBOM is a software, just BOM is Bill of Materials, is about hardware. So basically inventory. Yes? I don't hear it at all. E2EE, end-to-end encryption. Okay, let's do it like one more. Yes, please. RA, this one, risk assessment. Yes. H, what? Okay. So we have the winner here, actually, this gentleman on the second row. H and Y, it's a Happy New Year. It's not related to security. All other things. Thank you. All other things were related to security, and some of them you learned today. I hope this talk was useful for you. I hope you learned at least something new, or at least you have some information to Google and to read during long winter holidays. If you have more questions regarding security, drone warfare, protecting huge systems, please reach out. If you will not find me on the conference, please connect to the LinkedIn, Twitter, or whatever. If you want to go and work on mission critical, high risks, high stakes, very interesting systems, we have a lot of positions open. And thank you for your attention. See you here somewhere.